Welcome to our pre-AP notes on ionic nomenclature. Ionic nomenclature can be involved, so we're going to take it one little piece at a time. To start off with, how do we even know to use ionic nomenclature? Well, we use it for ionic compounds, and they're going to be between a metal and a nonmetal. So if you have to cross the stair-step line to make the compound, it is going to be ionic. The reason we need that is because metals have high electronegativity. They're strongly attracted to the wow, I said that backwards. Sorry. Nonmetals have that high electronegativity. They're going to be strongly attracted to the electrons of the metal and pull them away from the metal. That's going to leave metals with a positive charge and the nonmetals with a negative charge, and opposites will literally attract. So, for instance, with sodium and chlorine, again, chlorine being the nonmetal, can pull with its big electronegativity on that electron from sodium. Sodium, by its nature, can't really pull on that as hard, so who's going to win this tug of war? Obviously chlorine. So that electron transfers, and now sodium has one less electron than it used to, and chlorine has one more electron than it used to. That's then what gives them the charge. 11 positives and 10 negatives mean a positive 1 is left over. 17 positives and 18 negatives mean a negative is left over. They then literally stick together magnetically. We call it an electrostatic attraction, but it is positive and negative. Opposites attract, they're going to stick together. That is the ionic bond now. So the transfer of electrons comes first, and then as they stick together as magnets, that is the ionic bond. Okay. Now they do this in a way that actually works well for everyone involved. It is a way to lower the chemical potential energy of the atom. We know there's a special group of elements that already have the lowest chemical potential energy of all the other elements. They're the noble gases. So giving sodium to lose an electron, here it is with one electron, here it is without one electron, makes the electron amount the same as neon. Now, it does not change the fact that it is still sodium. It just lowers the potential energy lower like neon. With chlorine, we are not necessarily close to neon. We're really, really close to argon. By gaining one more electron, it gets an electron configuration just like argon, lowers that potential energy. That's why it works. That's why it does it. Just like a ball rolls downhill, the elements like chlorine will gain electrons to go lower in energy. Again, it makes chlorine does not turn chlorine into argon, but it makes chlorine have the lower chemical potential energy that argon has to have their electrons work out the same. So it works for both. Okay, so metals will have enough positive charge to be like the previous noble gas. Nonmetals will have enough negative charge to be like the next noble gas. Allows us to start counting those charges right off the periodic table. So when they get together, they will naturally do this in a way that makes the overall compound 0 in charge. So if sodium's a positive 1, chlorine's a negative 1, a 1-to-1 ratio makes that neutral. Magnesium being a positive 2 and sulfur a negative 2, again, it's a 1-to-1 ratio to make that neutral, or 0 charge, because that's what a compound's going to do. With aluminum being a 3 and nitrogen being a -3, neutral, 0 charge overall. What if they're not the same? If I add an aluminum to a sulfur, I still have a positive 1 charge. And you're like, okay, so I need some more negative. So let's add some more sulfur because we have nothing but aluminum and sulfur around. Let's add some more sulfur. Well, if I add another sulfur, I have a positive 3 and a total now of -4. That leaves me with a -1 charge. You're like, okay, let's add some more positive. I have aluminum around and sulfur around, so I'm going to add more sulfur. So now in a 2-to-2 ratio, I have a positive 2 charge, so I need some more negative. I'm going to add some more sulfur. And now I see in total, I have a positive 6 charge on aluminum. In total, I have a -6 charge on sulfur, and that's going to neutralize the compound, make its total charge 0, which is what we want. How many aluminums did it take to get there? 2 of them. How many sulfurs did it take to get there? 3 of them. That's what those subscripts represent. The amount of atoms in that compound that are needed to neutralize the whole compound. And nature will make the compound neutral. We just need to note the ratio, because nature doesn't then tell us, oh, by the way, the ratio was. It's up to us to figure that out. So 2 aluminums, 3 sulfurs in the compound of aluminum sulfide. Here's a shortcut. What do you notice about the number there, and the number there, and the number there, and the number there? Well, this works all the time, so we even have given the shortcut a fancy name. We call it the crisscross method. So notice how those numbers literally flip. What students want to do all the time incorrectly is say aluminum was a 3, sulfur is a -2, and move the 2 down there and the 3 down there. That's straight down movement. That's not a crisscross. Don't do that. It is called the crisscross method for a reason. You have to get those numbers to flip past each other. If you use the crisscross method, it does work every single time, as long as afterwards you see if you can reduce. Notice how with aluminum and nitrogen, 3 and 3 reduced to 1 and 1. So I'm going to do that. And we don't write 1s. It saves us time. Like in math class, we don't write 1x when we start writing our equations. We just write x. Same thing. It's a little shortcut to save us time. Also, we will always write the metal first. The non-metal is always second. The positive part goes first, the negative part goes second. It will always be that way. You will be incorrect if you don't do it that way. So now that we have formulas, let's name them. Here's the nice part. The only difference is the ending. What's Li? Lithium. What's F? Fluorine. We change it to fluoride. Add the ending of I to let us know they're not 2 separate elements, they're now together in a compound. What's Ca? Calcium. What's Br? Bromine. Let's change that to bromide. Where in this name do I mention that I have 2 of them? Nowhere. The little numbers for ionic bonding does not make a difference in the name. So be sure you note that. So naming them is real easy. Going from the names to the formulas, that's where you write the elements, you crisscross and reduce. Now we're going to make it a little more complex by adding in polyatomic ions. So polyatomic ions are ions made up of many atoms, hence polyatomic. Overall, they have a charge. Here's ammonia, here's hydroxide, here's carbonate, here's sulfate. Somewhere in these drawings are some either extra electrons or lacking electrons. Where exactly, we actually would never know, because an electron looks like an electron, whether it was there originally or not. What we're going to do with them is actually the exact same thing we used to do, with a few minor changes. We still crisscross and reduce. But if I crisscross, and I'm going to crisscross to a polyatomic ion a number greater than 1, I need to put the polyatomic ion in parentheses before I put the number on the outside. Because that number truly does then get multiplied. I want to say I have 2 arsenate groups, not just if we didn't have the parentheses, check out what it looked like. We'd be saying, instead of arsenate, we'd be saying whatever AsO42 is. And that is so not what we want to say. We want to say we have 2 arsenate groups. All right? Just like a rock band, everyone's sad when the rock band breaks up. Don't break apart the group. If it is a group, it needs to stay as a group. Don't break it up. Naming it has a small change in that we don't change the name of the polyatomic ion. Li is lithium. C2H3O2 is acetate. Notice, no name change there. I just say lithium acetate. NH4 is ammonium. OH is hydroxide. I did no name change there. Now, what if it was NH4Cl? That would be ammonium, no name change. But now ending with a normal element, I would change that to chloride. So we only change the ending on elements when they're on the end. For polyatomic ions, their name does not change. And then what do we do about those metals that can have more than one charge? Those ones that are in the inner transition, the transition and inner transition area of the periodic table. And that's not to say that all of these have more than one charge, but most of them do. Well, we need a way to name them that specifies what charge it is being at this moment at this compound. So the old method was called the classic system, and it used suffixes of us and ic to let you know whether it was using its low charge or high charge at the time. This made for some interesting sounding element names. We have cobalt would be, if it was +2 at the moment, it'd be called cobaltus. If it was +3, it'd be called cobaltic. Copper, if it was +1, would be, it's not even copperus. It goes to its Latin name, cuprus and cupric. And gold, its Latin name, and iron, its Latin name. Needless to say, this was quite confusing. You do not need to know the classic system. It is on its way out. It is not being used as often as it used to be. I expect in the future it not to be used at all. However, I wanted to just show you it in case you ever run across it, because every once in a while I actually do see a label that would say something like cobaltus instead of cobalt 2. The new system, the Stock system, named after Mr. Stock, who invented the system, uses a Roman numeral in parentheses as part of the name, whereas that Roman numeral exactly matches the number. It's no longer high and low, it is number for number. That's the charge, that's the Roman numeral, or that's the Roman numeral, that's the charge. So it really does simplify things, and this is the system you need to know. So, if we have the name and we want the formula, the number will tell us what the charge is, and we crisscross reduce. It makes it more involved when we have the formula and we want the name. The formula between iron and oxygen can be two different forms, because iron can be either a +2 or 3 here or a +2 or 3 here. Let's figure it out, and this always works. Trust me, this will always work if you go in this order. First, I like to just draw a divider line between the positive metal and the negative nonmetal. Your nonmetal will always only ever have one possible negative charge. Of all of them that I've had you memorize, trust me, there's only one negative charge. Yeah, there might be lots of positive charge, but it's on the end of the compound. It must be negative, use its negative charge. Oxygen is a -2. I have one oxygen, that's a total negative of 2 on this side of the compound. Now the compound must be neutral, so I must have a +2 to neutralize the -2, and I have one iron, so that's a +2 for each iron. I name it iron 2 oxide because iron has a +2. Doing the same thing over here, each oxygen must be a 2, but I have 3 of them, so this is multiplication. -2 times 3 gives me an overall of -6. To neutralize a -6, my irons must total +6. Oh, but I've got 2 of them. This is division. 6 divided by 2 means each iron is individually worth 3. Now I know I have iron 3 oxide. It always works this way. Start with the negative charge, multiply by how many you have, neutralize it, divide by how many positives you have, and you've got your number. I call it the rainbow method because you can see it kind of makes a rainbow. But you have to be left-handed to make your rainbows. I'm just joking. But it always starts on the negative side. So start your rainbow on the negative side with the charge, then multiply, then neutralize, then divide. If you do always those steps, you can never go wrong with it. So again, I wrote out in words exactly what I just showed you. So you've got both ways of learning that. Good luck.